Dear students, welcome back in lecture 3. Students, in this lecture, inshallah, we will discuss about question number 2. As in question number 1 and 2, we cover question number 1 of the major assignment. And right now, we see question number 2. So, this is an analysis question. We have a given design beam is given, which is a section 10-12 section. And we have to just check the compact section, whether it is a compact section, and we have to check the design flexural capacity, which for both LRFD and AISC. Okay. Now, to know to start to design, to check to analyze this question, we have to know some basic terminology, which is a compact section criteria. Now, what is a compact section criteria? What is a compact section, non-compact section, and slender section? So, turning toward this basic concept, I want to show you some interesting material. So, let us discuss some basics. Clear? Watch this video. Okay. In this video, this one. Okay. Now, the very important detail which is in this video is this one. You see the beam right here, you see the beam right here, and you see the beam right here. Clear? Now, you see the flange is basically buckle out. Okay. Here you see the flange is basically buckle out, and here you see the flange is basically buckle out. So this kind of failure is basically known as local buckling. Okay, because you see the whole beam is not failed, only a part of the beam, that is a flange, is buckle out. So this is called local buckling. Why this kind of local buckling is happen? This is interesting, and we understand this one. One of the most important other detail is right here. Okay, you see the flange is buckle out, clear, and here in column you see the flange is buckle, clear. You see this one. So this is called local buckling of the member. Okay, why it has happened? It's all due to the compact and non-compactness of the section. Okay, now let us watch in another video, and then we back to.
There's something I've always wanted to try. To make something really strong out of weak materials. This is not a strong beam. I'm going to use always wanted to try. To make something really strong out of weak materials. This is not a strong beam. I'm going to use super thin plywood and styrofoam to make a beam that can hopefully hold up a load of hundreds of pounds. It's an I-beam. This is the classic I-beam. It's called an I-beam because in cross-section, it looks like an uppercase I. I need some inspiration.
A very important thing which is I want to discuss with you, that the parts of
uppercase I
beam. Clear?
I need some
see there. This is the flange of the beam, and this is the web of the beam, and this is also a flange of a beam. You see, this is the width or breadth of the flange, and this is the depth of the web. And you see, this is the thickness TF of the flange, and this is the thickness TW of the flange. And if you basically see this in manual, you see here the thickness of the flange, the width of the flange, BF, thickness of the web, and you see the depth of the web. the ratio of the flange width to 2 times thickness of the flange. You see this guy right over here, this one, okay, is called a slenderness ratio for flange. And similarly, the thickness, the ratio of the depth of the web to the thickness of the web, that is h divided by tw, is also called slenderness ratio for web. So slenderness ratio for flange and slenderness ratio for web. We use this in example in question number 2, but you up to this point you must understand what is this. This is a slenderness ratio and it is denoted by lambda. Okay, lambda f and lambda w. Okay, now back to the video.
Inspiration, I want to see some I-beams. The reason you're going to see these everywhere is it's the most efficient shape we have for making a beam as strong as possible while using as little material as possible. Now imagine this is the top of the I-beam and this is the bottom of the I-beam. When we apply a load to the middle, it bends. And you can see the screws on the top of the beam, they get closer together. The top of the beam is in compression. Now look at the screws on the bottom end of the beam. Those screw heads get further apart. That means the bottom side of the beam is in tension. We want to put all the material where it's needed the most, at the very top and the very bottom of the beam.
This is very important data they want, because almost we have maximum bending. The beam is basically primarily a flexure member, so basically it is designed to support to bending, and almost all bending is basically occur at the top, because we understand basically the flexure formula. As we know, moment MC is nothing, it is basically stress times moment of inertia divided by the central distance, or you can say the fiber distance, that is basically your C. Now from the centroid, from the neutral axis to the top line, this is C. No, but the very important relationship from this equation which we understand is basically movement is directly proportional to moment of inertia. Now the flexure capacity, you can say movement is nothing, it is Mn. This is nominal moment capacity. It is directly proportional to Ix, moment of inertia. Now we need to increase the moment of inertia. How to increase? By locating the area of the section far away from the neutral axis, and this is neutral axis. Now if we increasing the area of the section is far away from the neutral axis, we are increasing the moment of inertia, and thus if you are increasing the moment of inertia, your nominal moment capacity or the strain capacity is increasing. Very important. And you see this in this video as well, that how they increase the distance, okay, basically. So let's see.
If I tried to stand on this as a bridge, it would break in half a second. But it's still strong in a couple of other ways. If I were to hang on this, it would support my weight no problem. It's decently strong in tension. Now wood is especially strong in compression. If I were to hold this upright and stand, if I were able to balance, it would also support my weight no problem. So what if there was a way we could build a beam that loaded this up in just tension and just compression? It might be able to hold. So I've taken the 2 pieces of plywood and styrofoam in the middle and built an I-beam out of it so that the plywood can do what it does best. Take compression on the top and take tension on the bottom. Hopefully, it'll hold my weight. I'm really careful when I'm working with weak materials. See, I'm not far off the ground, so I won't hurt myself if the I-beam fails. Also, I'm starting with my feet out at the edges and slowly moving them inward to make sure it can hold me. Not too shabby. I'm probably about 160 pounds right now. Not too bad for a couple pieces of styrofoam and plywood. So what I've done here is built up the same beam, same amount of plywood on the top and the bottom, but I doubled the thickness of the styrofoam in between. The further out the top and the bottom are from center, the more leverage they get to resist that load. That geometry is so valuable that when you double the height, you can get...
This is the principle which I want to show you, that you see how the distance affect, okay? You see here, there is neutral axis, the distance is small, but here, as they increase the distance, they say that it will tax 2 times more load as in this case. So that's why, because here we are locating the whole movement of the area of the section as far away, because this distance is more than this one. Here the cross-sectional area is close to the neutral axis, but here we increase the distance, and that's the basic principles of I section beam, which is the most effective and efficient section of the beam. Okay, so they basically show you the concept behind the I beam.
More than a double increase in the strength. I'm using a hydraulic engine hoist and a big stack of 45-pound weights. So remember before, we had the I-beam with the single layer of styrofoam, and that held my weight, which is a little over 150 pounds. We're about to see if this double-sized beam can hold 400 pounds. Ready? Coming down. Nice and slow. Oh yeah, that's holding. So for only a double increase in the height, going from 1 to 2, we got more than double the strength increase. Like an I-beam.
This is the principle how things work. Okay, now we are what lecture notes I will use. These are the lecture notes, okay, which I use. These notes are available on Google. You people can search it and can download it. Okay, the topic is basically right here is local buckling, clear. And here we have to understand local buckling. You see how local buckling is occurred. Why it is occurred? It is due to the concept of compact and non-compact section. Okay. Now, very important term. I discussed this graph with you people. Okay, very clearly in lecture number 1. We have 3 distinct region in this graph. The first region is basically a plastic region. This one is an elastic region, and this one is elastic region. If the strength of the section lies in this zone, basically, the section is basically develop full plastic movement, and the section is known as compact section. Okay, and the element will be a compact element if its flange is compact as well as its wave is compact. What is compactness of flange and wave, we will discuss it in this question as well. But the design moment capacity, if it is less than MP but greater than MR, so the section will lie in this zone. It will not develop its full plastic capacity, plastic movement, and the section will be as a non-compact section. Okay, and if it comes here, then the section will be a non-compact element. Okay, so basically these are the basics. What is a compact section, what is a non-compact section. Okay, and how to check a section, that whether it is a compact section or whether it is a non-compact section. A very simple procedure you have to follow. You have to calculate a lambda value. Lambda is nothing. You have to find lambda for flange as well as for wave. For flange, it is defined by B by 2TF. You can select it from table. For wave, it is H divided by TW. You can choose it from table. Now, these are the limiting values, that is lambda P and lambda R. These are the limiting values which make a section compact and non-compact. So lambda P and lambda R is basically these limiting values. You see here, if your lambda is increasing, this means you are basically going towards inelastic region. Inelastic and elastic region. If your lambda is less than lambda P, this means you lie in a plastic region, means your moment capacity of the section will be MP, means that the section will be a compact section. Now, if your lambda lies in between these two, this means your section not developing its plastic movement. Okay, the section will not be a compact section, the section will be a non-compact section, and its strength will lies in between MP and MR. Okay, we have to calculate then by a formula, and that formula, let me show you. That formula will be, let me show you this one. This formula, we will calculate in second zone, that is a second category beam, and we calculate the strength capacity of that section by this formula. Okay, now very important. Okay, now turning to this value. Okay, and if your lambda is more than lambda R, this means you are in elastic zone. And how to calculate moment capacity, that is third class category of beams, and we will inshallah do some example on that. Okay, so that part I already show you those formulas in lecture number 1. Please watch that lecture. Okay, now very interesting, lambda p lambda r, this 0.38, if you multiply it with e into root, you got 65. So if you can use this by 65 divided by fy under root as well. Now let me show you. If you multiply e into root with 0.38, you got this term like in this fashion, 65 divided by fy under root. Clear? 65 divided by fy under root. Okay, and similarly, if you multiply 0.3 with e under root, you got 170. So then you will use for lambda r 170 divided by fy. This is fy, not fl. Clear? And similarly, if you multiply 3.76 with e under root, you got I think so you got 640 divided by fy under root. And if you multiply this with e under root, you got 970, I think so, divided by fy. We use these formulas because I don't use these formulas, although you can use these formulas, but in example I will use those. These are basically limiting values, and these are selected from the manual. So you can search these formulas in table 5.3 in your LRFD manual as well as in your AISC manual. Okay, so I will show you inshallah these formulas as well, okay, in my next lectures. Okay, now let us turn toward the example. Okay, we have to satisfy W10 for compact section criteria and design flexural criteria. Okay, now from manual table 1.1 we have to select B by 2TF. How it works, let me choose. This is AIC manual, and where is W10 section? Where is this one? Basically it starts from here. The last one is W10 by 12, and here we have B by 2TF and H by 3W. We select these 9.4 and put 6.6. This is basically lambda W, and this is basically lambda F, okay, for 12 and this section. Now here you see this is B by 2T 9.4 and this one. Now checking flange, okay, this is lambda PF or lambda F, and this is lambda F and this is lambda W. Now 65 divided by Fy under root, one can use that formula as well. This one 0.38 E divided by Fye, just 29,000 KSI, or you can say 29 × 10⁶ PSI. Now I use 65 divided by Fy under root. This is lambda PF, okay, lambda P, you can say lambda P, this one, okay. Now this is lambda P. Now I have to check this lambda P with this lambda. Clear? As this one is less than, means that lambda is more than lambda P, and that's why we are in second zone, because our flange is non-compact. For a compactness of a section, it is necessary that both flange and web are compact. So here we have to check, although flange is non-compact, we check the web as well. So lambda W, this is basically lambda P, 640. One can use that equation as well. This one, okay. One can also use this equation as well, okay. So basically I want to show you these differences, because most of the books use these formulas for just checking the section, okay. So one can also use these formulas as well as those formulas as well, okay. Now we calculate the lambda W to check the web. We see that lambda for, you can say lambda for the wave is less than the lambda PW. So that's why, although your wave is compact, but your flange is non-compact. So for a compactness of a section, it is necessary that both flange and web are compact. So that's why on the basis of on the basis of the compactness, non-compactness of the flange, we say that the section is non-compact. Now to find out the flexure capacity, we have to use, because as the section is non-compact, so the section lies in second zone, that is the inelastic zone, and I show you that when a section is basically lies is a non-compact section, you have to calculate the strength of that section by using this formula. Now what is this formula and what are the terms? That means basically MP is equal to Zx. You have to choose your Zx from your table. Let me show you the table. You have to use Zx. This one is Zx, and here you have the section. Zx is 12.6, and also we have to use Sx, that is the elastic section modulus, and the elastic section modulus is 10.9. So let me show you. Zx is basically 12.6, and multiply these terms dividing by 12 to convert it into feet. You got 52.5. This is MP. Okay. Now this MP value is 52.45 something. Okay. Now 5. Okay, 52.5. Okay, feet. And now we have to determine this MR, because the section strength will be in between these two values. So MR is nothing, it is just only 0.75 times Fy times Sx. Okay, 0.7 Fy Sx is elastic section modulus, 10.9 from table. I will show you this one as well. Here you have Sx, and that is 10.9. Now we have MR, lambda, we have B by 2TF, we have lambda PF, that is a limiting value, and lambda RF, which is another section slenders parameter, and this is 170 divided by Fy under root R. One can use this formula for, as this is flange, for flange, so one can also use this formula. This is for flange, 0.38 divided by Fy under root R. One can use that one. Okay, this one 170 divided by Fy under root. So your lambda RF is 24.1. So we see that our lambda is more than this one, okay, but less than this one. So this is a second category beam, or for second category beam we have to use this formula. Clear? Just plug the values you got, okay, for MP, MR, lambda PF, and you get your desired answer, that is your M. Now very interesting terms which is very necessary to understand, that your M in, this is your non-moment capacity. From the graph it is clear that the second category B's strength lies in between two values, MP and MR. So your strength NM must be greater than MR but less than MP. So you have to check it. Okay? Our MP value is basically 52.5, so our value is less than, and MR value is basically that is 31.8, so that is greater than that value. Okay, we have to convert this into design capacity by just multiplying the reduction factor, that is 0.9 to 6.96 feet, and if you want the allowable capacity, that is the AISC method basically. Here in LRFD we have to multiply with the reduction factor, but in AISC method we have to divide it by a factor of safety, and that factor is 1.67, then divided by 1.2, which is the design allowable capacity. This ends of this example. Now, this is the LRFD manual procedure. If we use AISC manual, okay, so how we can do this example? That is a more simple procedure. It explains the whole thing in one paragraph. Okay, so let me show you some important data. Okay, this is AISC manual. Okay, you see the graph over here. We have a compact section, a non-compact section, and an elastic section. You will see MR and MP. The strength, which is in our case, is MP dash, which is in between MP and MR. And you see the formula as well, and you see these lambda values. Okay, lambda, what is lambda? Lambda P, I will explain. And similarly, I also explain this terminology in lecture number 1, what is LB and LP. Okay, basically LB is unsupported length. You know, it's an example 1. I will and LP basically it is also calculated from a formula. Okay, this one is LP, and we can also select these LP and LR. These are the limiting lengths basically, also from the products. Okay, now we are do the same example by using the AISC manual. So to do this the same example by AISC manual, we have to come to a ZX table, clear, table 3, 2, clear, and we have to search the section, and we have to find out the design string, clear. So by just dragging the table, you see the W10 section right there it is, this one. Now you see the small f just above the tab. Okay, this is basically what it means. You come here in the down, okay, and you see f shape exceeds compact limit for flexure with f equal 50. So we were a design string f60 50 this section basically is a non-compact section. Non-compact due to plane, not due to width. It means due to plane. So you got your first part of the answer, that the section is non-compact. Okay. The second thing is the design capacity, and that is the PBMX, or you can say P pi into M. You are like this term, basically this one. This one is 46.9, and you see right here this one 46.9. Okay, so this one is basically, and those LP and LR I will do them examples on this. Okay, but those are the limiting values you got from this. So this is the way how we use AISC manual. Okay, and this is the way that how we are used LRFD manual. Okay, so in LRFD manual basically things are we have to use basically a little bit numeric theory formulas, but by using AISC manual you can do the things so easily. Very important terms so share with you. These notes are very important. Okay, you can download it from Google, and the book is also in lecture number 1 I share this book. Okay, this is the WCG book. Okay, and a very interesting book. Okay, this is the author. Manual is available on instruction manual is available on Google. Okay, you can download it. So this ends of this example. Okay, in next lecture number 3 basically, in lecture number 4 sorry, I will do the question number 3. Okay, that is related with CD. Now here up to this point we don't use the CD value. In next lecture inshallah I will do this example. What is CD? Basically the string which we got here is multiplied by a factor that is CD. Okay, and what does CD mean, why we multiply it? So please watch lecture number 4. Up to this point, if you have any question, any suggestion, please share with me.